Hey there, everybody. This is Kit Merker here from Noble 9, and I'm with Les Lincoln. He's an SRE at Microsoft, and we're going to talk a little bit about reliability.
Hello.
We were talking off camera a little bit, and one of the areas I think is really interesting, you were sharing about the evolution from sort of data center to cloud. What's changed? What's the evolution been?
We are constantly seeing this back and forth, right, between uh, having distributed computing and having centralized computing, right? And so, I mean, you saw that with the advent of the mainframe, right, where everybody had to go to a building, and then you're like, well, maybe I'll put a remote terminal somewhere. And then finally, you're like, well, I've got enough power at this remote terminal to do some computing before I, ship that off to be done elsewhere. Um, and you see that again, with the advent of other people's data centers, right? So, there's a brick and mortar. They might have a data center that they use to do some of their local compute, but an executive wants to do some Excel work on their desktop or whatever. And so, again, there's kind of that tie in between those two things. And then now we're kind of seeing the same thing with the evolution of cell phones, where you've got a lot of local power in your hand, but you can't hold everything in your phone. So you still have to get, back to somebody's data center. But now we're kind of centralizing those data centers in the cloud, right? So what used to be a tier 1, tier 2, or tier 3, regular data center has now really kind of migrated that main set of processes to the cloud.
And you personally have been involved in building out some data center infrastructure, right? Like, what's that experience like, especially when it comes to how people might want to use your resources and getting developers to be productive in your data centers?
I've been really fortunate to build a number of data centers, right? My first experiences around that were with Mindspring/Earthlink, when the great ISP integration happened, right? And so there was actually one point where Mindspring bought this company called OneMain, which was 1,000 mom and pop ISPs, right? So we basically integrated all of their services into one data center, and then had to expand that data center a couple of times. That was really interesting because that was a traditional kind of tier 2 data center where there's raised floor, there's cabling under the floor, you've got a bunch of HVAC, there's generators on the backside of the building. And you're thinking about, how are you going to have redundancy between this facility and another facility? And the easy thing to do at that time was actually buy somebody else's facility, right? So now you have Mindspring on one coast with one type of data center that is quote unquote tier 2, tier 3 now. And then Earthlink on the other coast, which has a completely different data center infrastructure that's also tier 2, tier 3. But you're like, are they truly redundant, right? Can I actually migrate services from here to there or there to here without really some consternation, right? So you kind of have to backtrack through all of those differences and make sure that you have some parity that you can count on.
What's the new way that has resolved that issue? And is it even easy to migrate and have apps that can move to multiple data centers?
It is, man. And this is a really interesting topic for me. I'm an old VMS guy. I like VAXs and digital equipment stuff because they pioneered a bunch of this stuff, right? There was the ability to move live loads between nodes on VMS, like way back in the late 70s, early 80s, right? And so we've replicated that with things like VMware or Kubernetes, et cetera, right, to kind of get away from the hardware layer. But it's always amusing to me because we've kind of reinvented that wheel, right? That wheel already existed, and we're like, no, we'll do it all over again, right? But what that means in the data center world is that as long as your compute infrastructure is reasonably homogeneous, you can actually move stuff from here to there. But there's a bunch of other signaling that has to go into that so that how much reserve capacity do I have? What's the size of this application? How much compute does it actually need, right? What's the resiliency factor for that? And really, what's the capacity, right? We used to have this problem at Google all the time where there would be an application that would reserve way more machines than they actually needed because, machines fail, right? Entropically. And so sometimes if there's no technician to get to that machine overnight, you might get to the point where your service is teetering on failure, right? So they would just get extra machines, but that means you have to pay for those extra machines. You have to pay for the extra data center to run all of those machines, all of the HVAC and everything that goes along with that. So trying to minimize that margin as much as you can is really important these days.
Is that kind of a tragedy of the commons? Like, how do you resolve that conflict, I guess, between having redundancy and reliability versus the cost of the infrastructure?
You really have to know a lot about your application, right? You have to know kind of what the minimum needs of the application are, and what's the max capacity that you have seen historically or might see in the future. A great example of that is when Michael Jackson died, right? So all of a sudden the internet just lit up, and everybody's edge services were like, whoa, what happened, right? And that's because you don't necessarily plan for a full capacity usage like that. And we're seeing that today, right, in the middle of the pandemic, where all of a sudden everybody's at home, they're online all the time. Comcast is like, wait, you can't use all of that bandwidth at once, right? And the same thing for certain applications. I know of a number of people who were concerned that they could not get to their work because their VPNs were not sized for everybody to be on at that particular time, right? But so when you're thinking through these max capacity plans, especially at cloud layer, right, you're looking at what's my normal usage fingerprint for a week or for a month, because some of them are monthly cycles. And then, what's my growth expectancy for, the next year for that particular application.
Les, I want to ask you a philosophical question.
Sure.
Why is reliability hard?
I can think of a couple of reasons that reliability is hard, right? One is that there is a nebulous area of diminishing returns, right? If you start to get more reliable, it gets way more expensive. And quite frankly, humans are bad at planning for things that they don't think are going to happen. I think the other reason, though, is that we also generally have been trained in the internet industry to fight fires, right, instead of prevent fires. So, we're like, what, that might go bad, but I'm a great enough engineer that I'll just handle it when it happens, and everybody, it'll be fine, right? No.
The firefighting point is really interesting. I think there's a little bit of a mindset around feedback loops, right? Where you want to say, okay, let's create continuous improvement. Let's get better, right? So you have a system that's complicated and prone to failure, but if we can monitor it, we alert on it, respond to it post-mortem, that eventually, doing that enough times will reach a higher level of reliability. Is that the best way? Is that like the right kind of way to think about the methodology of achieving a highly reliable system?
It's part of the foundation of that, right? But there's that mindset of continuous improvement. But we don't always incent that mindset. We actually incent people to be heroic and put in heroic effort, right? And part of that is, it's expensive to pre-plan for reliability. Unless you spend the human capital up front to figure out, number one, what's my reliability goal for all of these systems combined, right? And then, how much am I willing to invest in order to make that happen? And how have I communicated that to the people that are actually, engineering or operating these systems? And the reason I say it that way, right, is that this is one of the key functions of SRE, is that when problems happen, SRE are supposed to step in and say, okay, let me figure out why this happened, and then let me automate my way out of this so that it doesn't happen again, right? But frankly, that's, and admittedly, sometimes you won't see these problems until you're actually operating, and so that's a great reason to have SRE around. But many times the problem is actually just designed into the system because folks didn't think about how it was going to operate.
What do you think the biggest misconception is around SRE as a role? What do you think the difference is, or how would you explain the difference between SRE and other operational or IT ops types roles?
I think there's a couple of differences, but the perception is that many times people are like, oh, SRE are here to take my job. And you're like, no, I'm not actually here for your development job. I'm here to to help you operationalize things at scale. And frankly, we want to know as much about the way that people develop things so that we can have a bidirectional conversation about how do you operationalize what it is that you're actually building. It's really difficult to grow SRE as an organization unless you start it kind of at the same time as you start your cloud project, right? So sometimes there's this conception that you can go get some people that are interested in SRE and then kind of pump them full of compute steroids essentially and put them to work, right? But I found it most effective when you have someone who is already senior or principal in a particular discipline, and they are close to senior or principal in a second discipline, and then you put them kind of in place adjacent to that development team. It is possible to grow SRE. I mean, any number of people have or firms have had efforts to do that, but it just takes a long time, and it takes a long time to actually get to that level of familiarity with a discipline, whether that's networking or software engineering or cybersecurity. Take your pick. Right?
So you were talking about a little bit earlier about communicating reliability goals to the people who are actually operating. Diminishing marginal return on reliability investments, it gets more expensive. Meanwhile, the business leaders, the people who are kind of focused on customers, users, bottom line, they obviously want maximum reliability, as their intent, right? So if they talk about reliability, they're going to say, hey, everything should be reliable. It should be perfect. It should be fast. Don't embarrass me in front of customers, right? That kind of mindset. And they may be even thinking that they're promoting reliability. But my experience is that message is not very actionable when it comes to actually planning and deciding, well, what is the reliability goal of a particular service? How do you think about sort of the negotiation, if you will, between business stakeholders and technical stakeholders trying to agree on, the service level agreements, service level objectives, the reliability goals of the overall system?
So this is a really interesting question because it focuses kind of on where the original intent of that set of systems came from, right? So we were talking a little while ago about old school data centers, tier 2s, tier 3s, that kind of stuff, and they were really designed as islands, right? Because you're like, okay, this is my little island fortress, I can't let it go down, and so the interlock between systems and processes around that was fairly detailed, right? And so that detail really allowed people to say, hey, my method of procedure for doing this particular operation is going to be this, right? And then if I run into a problem, then here's my backup plan. And if I really kind of get wedged, then I can fail over to another data center in this particular manner until I can fix this, right? The cloud is different than that, right? The cloud is actually built to expect failures of compute, right? And so you have these failure domains where you're like, okay, if I lose this particular machine, that's no big deal. If I lose this particular data center, it shouldn't be a big deal, right? And so the resiliency is kind of built in at the base layer of that. Now, what's interesting is that even though we say that that's true, in many cases, we haven't really thought through all of the failure domains or interlocking failures of that until much later down the road, right? And so when executives are making decisions around where they want to spend that money, my vote is spend it up front, right, and design a resilient system rather than trying to retrofit resiliency into a system, because that's almost always much more expensive. And I'll give you an example of what I'm talking about, right? One of the things I really took away from my time at Google was that every data center was kind of a little bit different. They're all evolutions of a central philosophy for data center design, but the data centers themselves would have different physical plants or different versions of compute or something along those lines to fit the environment and to make sure that whatever it was that we were buying was basically the latest, right? So what that meant though was that from a compute infrastructure standpoint, all of these base layers had to be somewhat compatible, right? And so, if I was looking at taking a particular data center offline in order to do maintenance, then I need to be able to move to talk to my application and say, hey, can you move Gmail from this data center to that data center because this data center is going offline. At the base compute layer, even though those machines were highly similar, they were probably not the exact same type of machine because whatever data center was built last had newer stuff than whatever data center was built first, et cetera, right? So that meant that not only did the hardware have to be kind of homogeneous, but the software that supports all of that stuff really needed to be able to say, this application or Gmail needs this much cluster space to run. It needs this kind of network connectivity to these places, and the drain of it from this data center and the installation of it in this other data center. We know how to do that without necessarily making it a public affair. Right?
Did you say that sort of the Borg infrastructure, if you will, right, was the way to reduce the amount of kind of conversations, if you will, about this application needs to move to this data center because the data center people are kind of working in their own world of issues, and the application people working in their own world of issues on different schedules, timelines, et cetera. That was kind of the solution there, right? Is to have a homogeneous computing layer across all the data centers, regardless of the hardware, right?
Yeah, it certainly helped, right? I think there were a couple of iterations that we went through there because, first of all, no one wants to admit that you can't get your mail, right? So in certain cases, in the early days there would be like a manual data center drain to move a service from one place to another. And that's kind of where, SRE and other engineering teams came in, is to say, what, this is, not only is it stupid, but it's kind of fraught with peril. So let's see if we can't automate some of that risk away by, having not only, drain systems, but also kind of centralized brain like Borg, right?
Are you seeing the world right now through the lens of watching Google through this transition, right, from data center to cloud?
It is to some degree, right? I think, we've seen a number of pioneers in this area, like Amazon, Microsoft, Google, and Facebook even, I think, is really been a pioneer in this area, and to some degree Apple, right? Because you see Apple doing it, but they're doing it in their kind of own walled garden kind of way. Well, what's really interesting to me, kind of the evolution of private clouds, like some of the things you see at Rackspace, or when VCE was doing a bunch of, hey, you know what, you can get your own Cisco and EMC and VMware solution and roll your own cloud. That will help you solve some of your problems. Everyone basically faces the same problem, which is I have to get hardware agnostic, but I also have to trust that you know what you're doing with your hardware, so that when hardware failures happen, I'm either aware of them before they become catastrophic, or I've actually been able to avoid them because he told me before it happened.
So when you're taking a dependency on a third party, I think this is kind of gets to part of the crux of the issue here, is that you have a trade-off in some ways between sort of control and trust, if you will, right? So
yes. If
you control everything, that might feel comforting at some level, but at the same time, you don't get the economies of scale. You don't sort of get that advantage, right, that you would have from out, kind of pushing out or vendoring some of these things. But then at the same time, you come out on the other side of this conflict now and you say, okay, well, I'm going to have to trust these people. And then now I'm kind of at their whim, but maybe that's good because at the end of the day, you got a benefit and you got somebody to blame too. I mean, maybe that's part of the story as well. I don't know. What are your thoughts on that?
So there was a thought that came out of Xerox PARC, like, I don't know, in the 70s, around ubiquitous computing, right? And that's really what we're doing right now, is we're whipping the lumps out of the cloud, right? Because so there's 4 or 5 major clouds on the planet. Theoretically, you should be able to pick up your work job and move it from this cloud to that cloud. And there's some services that will do that for you, but it's way harder than it needs to be, right? And so the thing that I am working for, and this is actually part of the reason that I left Google to come to Microsoft, right, is I'm really interested in how do we get to a point where it's easy to move those compute workloads from one place to another, right? And I think that, and this also includes stuff that's on the edge of the network and stuff that's off the edge of the network, right? So, you've heard a lot about people doing compute in containers, or now there's compute that's at the head end of the cellular network, or even at the tower end of the cellular network, right? Not all of that compute is fully utilized, right? And so how do I get it to the point where I can move whatever work it is that I'm doing closer to where I am, so that my cycle time over the network is shorter, my security concerns are diminished, and that workload kind of agnosticity, if you'll allow me that word, right? It doesn't really matter whose cloud I'm on, right? I should be able to get whatever work done or information from other clouds easily in a secure and compliant manner.
It's an interesting utopia you describe. I mean, I think my question to that is it technologically feasible, given the competitive nature of the different cloud providers, the technology and compatibility, et cetera? I mean, I could see it working in certain use cases for sure, but is this something you see as imminent, or this is more of something that is still kind of a ways away?
I think it's still a little ways away, but I think the market is kind of forcing us in that direction, right? And it's one of those things that, quite frankly, most companies are going to fight kicking and screaming because of exactly what you said, right? So, but if you think of it as a market, right, like a transportation market, then all of a sudden it actually takes on a different dimensionality, right? Where you're like, I really just want to be able to charge for workloads that happen in my compute space, and for things that transit my networks, right? And I don't have to charge a lot for that, but my ability to be the go-between on compute jobs and network jobs, and even storage jobs, right? You might make a micro payment on that, on each one of those, but it becomes really lucrative when you look at how much traffic there actually is, and how much traffic there will be on the net. We're wedded to the kind of economic engine that we have today, but we're like, hey, that's coming. I don't know that I want to wait and be the last one on that train. I want to give you an example of like some crazy scale stuff that happened in one experience at Google, where actually two examples, right? One of the things that kind of took us by surprise at that particular time, Google had this interesting infrastructure where they put batteries actually on the server instead of the traditional kind of data center way, where there's a giant bank of batteries someplace and a UPS and a static transfer switch. They're like, you know what? We'll just put a small battery on the server, and it will be enough that it will carry the load until generator kicks on, and then we don't have this giant bank of batteries somewhere. We forgot to test those batteries. Right? So, we just figured, we'll just replace them every couple of years and it'll be fine, et cetera, et cetera. But I think we got a couple of bad batches of batteries, and so we had an outage, right? Because the power went down, the batteries were like, oh no, we're not actually good, and so all of those servers went down, right? The evolution of that though was, okay, so now we're going to test these batteries on some regular basis, right? Sometimes batteries test well when they're not actually good, right? And so, we went through this process again, where we realized that, the test had to be intrusive enough, not necessarily visible to the client, but that it had to be on load enough to tell whether or not the battery was good, right? So we went through that, right? And so now everybody is feeling really good about this solution, right? We're like, we've got new batteries, we're testing them almost to failure all the time, so everything should be fine. We had an outage, right? The batteries worked perfectly, and then we moved that load someplace else, and we actually let the systems go to failure, right? Because there was no load on it. What we didn't realize was that when we turned that particular data center back on, all of those batteries needed to be charged, as well as all of the power supplies for, literally tens of thousands of servers came on all at once, right? And this sent a shock through the system back to the power company called an inrush. And so now there's literally an electrical signal that is bouncing at, I think it was a 230 kVA or something like that between the data center and, you know, the power company, which caused the power company breaker to shut down. So all of a sudden, it's not just our problem. It's like a local outage for the power company, all because, you know, we didn't really kind of think through some of these challenges around the electrical engineering side. There were a lot of smart people that were scratching their heads about, you know, why is this particular thing so hard? You know, when frankly, you know, we could have just asked the electrical engineers at the power company, and would be like, don't do that. Right? we've already figured that part out. But, you know, because in many cases, engineers are used to being the smartest people in the room, they don't always ask questions of other people or other engineers because they're like, this couldn't possibly be a problem.
When I asked you before about like why reliability is hard, but you know, there's a certain level of humility and curiosity, it sounds like too, because you know these things when you just kind of run at them and are trying to solve problems without understanding the full context, right? It can be very, very difficult to get it right.
Yeah, absolutely. And many times these are quote unquote secret projects, right? And so it's tough to ask questions in a generic way and get the answer that you need. But I think more often it's just that we're just not we're not humble enough to admit that, you know, we don't know everything and we might need some help. We figured out that in order to get down the number of machines that any service needed, once they told us what that number was, we figured out that if we repaired machines in a certain order in the data center, we could always reach their machine just in time. There's an algorithm that needed to be put in play to figure out which services were closest to failure and which machines they needed repaired by when in order to make that happen. And what really kind of floored me out of that was it turned out that it was actually cheaper to have more people in the data center to make these repairs happen in the order that they needed to happen than it was to really figure out, you know, add a couple of machines here or there to each one of these services, right? So we wrote the algorithm and started to send techs to do particular repairs. And then we also realized that those particular repairs, if we had data on what the symptom was and what the actual fix was, we could automate that as well. So we went from a system that had some 30% compute overhead to a system that had 5% compute overhead. So 25% of the fleet became available to do other work instantaneously.
That's amazing. And what would you attribute that gain to? It's like it was the idea of applying the sort of software engineering to it and automating the problem versus throwing people at it. Was that the big change, or was there something else that drove that change?
It was that, and the realization that you know, it's very difficult to see the big picture because, you know, you're in a data center somewhere and you're like, oh, there's 100 machines that are broken. Let me start with machine 1 and I'll work my way to machine 20. And these data centers are enormous, right? I mean, 500,000 square feet is actually a fairly small data center these days, right? And so, you know, but when you think about that in terms of tech time, that's, you know, that's a good 5-minute walk to a machine. And that's assuming that you actually have the parts you need to fix that machine. So you might have to go to a parts depot and then come back. And so figuring out some way to not only sequence, you know, where those machines are as far as the tech is concerned, so that the tech is being efficient, but making sure that they also have the parts that they need before they leave the depot. That really cut down on the repair time, which allowed us to free up a bunch of machines.
It's an absolute pleasure talking to you today. Thank you so much for sharing these stories and for talking with me today.
Oh, it's my pleasure. Thanks for having me.
Everybody out there, this is Kip Merker from Noble 9 signing off.